Alright, the subtopic that we are going to cover, there are 9 altogether, 9 subtopic up to 7.9, and altogether there are 8 examples coming from our textbook, and another 3 additional come from the web assign. Now let's turn to the textbook, which is 7, energy of a system. For your information, when we start talking about the energy, now chapter 7 alone is not enough. It actually comes together with chapter 8, okay? It's under the same umbrella. Okay, let's have a look at what's given by the book. Okay, the idea of observation as a student, or perhaps our daily life. So in this book, they provide you a sandpaper and a piece of wood where rubbed against one another, and turns out that both becomes warmer. So the term warmth indicates that there is energy involved here, but in the form of heat. Okay, in the form of heat, tenaga, yeah. So why all of a sudden this energy is here? Okay, so here you will find that applying force to the sandpaper, or perhaps applying force with rubbing your both hands, okay, rubbing both hands, it accelerates and therefore changes in the velocity. And also not to forget that we have learned the idea of frictions. So these are all mechanics, alright? But this warmth, okay, so it has something to do with what we are about to see after this, which is called as energy. And to introduce the concept of energy, we're going to start with the idea of work. And bear in mind, when we start about energy, work onwards, everything will be a scalar product. So a scalar product is, hold on, a scalar product is without the direction. It's actually just value. On the other hand, something to note or to reflect what we have seen from chapter 2 up until now, chapter 6 previously, is all about the change. Velocity is a change in the position, acceleration is the change in velocity, while force is changes in motion. However, from here onward, chapter 7 and chapter 8 to be precise, you will find that one element here, we call it as energy, is conserved. It does not change. It does not change, but what? In terms of the total value. In terms of the total value. Okay, nilai dia sama. However, since you have seen this in high school, perhaps it's okay to introduce now, since it does not change. But what does change? It changes in the shape, but the total amount, numbers remain the same. So the energy of the entire universe, therefore, is fixed, same value at all the times. Okay, so quite contradict to what we have seen earlier in terms of the change in the position, because change in the position represent there's a change in the value itself. But here, energy, we're going to look at the idea that it does not change in terms of the number. But yes, you learn that it changes, but in terms of the shape. Alright? And in this case as well, we're going to go over again the idea of types of energy. So several forms of energy that can exist in our system, okay, surrounding us. So what are those? Stay tuned. And remember, yeah, okay, I did mention earlier that energy is a scalar, so it's just a number. So alhamdulillah, no complicated vector calculations. Now, before we start talking about the energy onwards, okay, we are going to start with one technique on how to calculate how energy is being used or converted, okay, and that is what we call as work. And to understand the concept of work, we are going to understand the concept of system and environment. System is our object of interest, and this object of interest will be interacting with who? Okay, so for this one, the discussion will be done while we are doing the concept of work itself. Now, the first method to discuss how energy changes is by using concept of work. Alright. Now, the easiest way to interpret what is work from a citizen, netizen view is energy being expended because you did something. Okay. So maknanya like for instance cleaning the house at the end of the 3 hours become flat. Energy used up. Why? Because you are doing work in a form of chores just now. Kerja rumah kan. So that is a generic idea of what is work. Okay. Now in physics however, we are interested with the idea of work whereby there is a byproduct, end product due to the work done. And in this case, we are looking at displacement. So, okay, we will see that the idea of work can be calculated by using this version. Okay, this version where work is done on an object, okay, on a system of interest by what? By exerting a constant force. A constant here represent satu value yang sama nilai. You don't change it. Then you can't use this rumus. Okay. To use this rumus, you must have a value that stays the same. Or else you can't use this rumus. Understand? Alright. And there must be times with a product of displacement. However, the displacement must be parallel with the force. Okay, simple analogy. Okay, you yourself push onto the wall. Though you find that you become tired after 30 minutes, that's not considered as work done. Okay, unless all of a sudden the wall start moving 1 meter, 2 meter distant away because of your force applied. Then that is considered as work. Understand? Now that goes the same with this figure. Okay. You find that let's look at C. Okay, let's look at C. Why? Because that's the easiest. Now this is where supposedly, okay, displacement should occur. Why? In the direction of the surface. Okay, either to the left or to the right. Never mind. But by pushing it, this is the force applied onto, okay, onto what? Onto the eraser. So the force here by your hand is the environment, okay, the environment, and applied to you, and due to that you're supposed to experience changes of something. But because there is no movement, we consider this as work as 0. Okay. Now, the two methods, however, A and B, will result a value of work. Okay, how do we do it? Okay, when we introduce you with the expression earlier, the work just now is defined as a product of F displacement. Okay, R is the displacement, magnitudes of displacement, and cos theta. The term cos theta here, you will find that F cos theta is here, right? Where this is the R. So in short, work can be calculated provided that is a constant value, okay? Constant value, and it must be parallel to the displacement just now. You can put it as delta R, you can put it as delta X, delta Y, so long that you understand it's a displacement product. Okay, and notice something as well. Though that the product here, the product of work is a scalar, but in terms of how to get here, it must be vector. So F is a vector, R here is a vector as well, right? Now coming back to the example above, okay, in this sense, we will find that if, let's say that this is 30 degree and this is the force, so yeah, we will find that there is a value of work calculated in this case, okay? And in fact, after this, you will find that when there is work, there will be a product of V, changes in V, right? And this goes the same as this one. Okay, it goes the same as this one. Perhaps the angle must be might be slightly larger than here 40. But at the end of the day, these two, they are trying to say is that there are work for A and B, but there is no work for C. Because why? There would be no displacement for C. Now, let's troubleshoot example 7.3. Now, in this example, we find that we have three forces that act simultaneously on this block. And we find that the block move a distance of R. Tapi isu dia, which of these three forces that provide the work? Okay, will give you work. It's only one sahaja, satu sahaja. Not this one and not this one. Why? Because they are perpendicular. So when it is perpendicular, substituting normal force cos 90 times the displacement will give you a product of 0. In short, there is no displacement due to the force of normal or mg with itself. However, we find that force exerted by pulling the blocks will result the movement, the motion, the displacement of the block. So, therefore, the system now move because the environment is acting force on the blocks just now. Now, to wrap up again the idea of work before we proceed with a calculation, okay, we will find that work is force time displacement, but there must be parallel. There must be parallel with one another, okay. And remember that R here could be delta X, could be delta Y, or even delta D. Any symbol so long that we understand it's a displacement product, okay. And another things to note as well, that F must be a constant value, one single value. If it does change, then we can't use the expression. Okay, so we must use a graph then. Okay, another thing to note, this is Newton, this is meter. So the unit is Newton meter and as well Joule. It's also correct to be Joule. Now, another consideration that we have mentioned earlier, work is an energy transfer. Changes of the energy from the system or something like that. Okay, so interaction between environment and the system that causes displacement. Okay, let's look, cause of this displacement. So we can calculate the work done. Yet just now, that force not necessarily the cause of the object displacement. Alright, so I did mention earlier that work can be calculated, number one, force time displacement, and they must be parallel, the unit is Joule, and this is the responsible factor why energy change, okay. And in this case as well, since energy change, speed change, we find that there is a displacement as well. So very much related to the kinematic actually. However, okay, for instance here in figure 7.3, we find that there are three forces but not all are necessary making the displacement. So this is the only one. Cause of displacement is just force applied at this angle only. Alright. Okay, let's now look at Quick Quiz 7.2. Now, in Quick Quiz 7.2, we are given four situations, A, B, C, D, where force are applied differently, okay, differently by somebody, okay, by environment to the system. System is the blocks here. Right, and they have the same magnitudes of F and same magnitudes of displacement. So you are to rank whether the work from most positive to the most negative. So here we learn as well that work can be negative. And something to recall back, work is negative meant for friction because energy is now turned or lost from the object. Alright, now let's have a look. Let's start with something so obvious that we do not need to do any calculation. For instance, the one here is 90 degree. So since it's 90 degree, product of cos 90 will give you 0. So hence work is 0 for A. Okay. Right. Now how about B and C? Okay, B and C. They are of the same value, but they are of different in direction, and therefore, okay, this will give you cos 180, which is a negative 1. And therefore, the amount of work will turns out to be negative F times delta R. How about this one? We are making comparison with this one. So it turns out to be work where positive, okay, positive F delta R. Bit confused. Okay, look at the angle. So as we substitute the angle between F and R is 0. So cos 0 is equivalent to 1. Means that the force, if we would like it to be a maximum value, it must be with the angle and parallel to the displacement. That will give you a maximum value of work. Why did I mention so? Because you will find, for instance, this one, I need you to troubleshoot with any angle, okay? So this is obviously bigger than 90 but less than 180. So let's just make it 150. So cos 150 is a negative value, but definitely less than 1. Am I right? Less than 1. Less than 1. Okay. Sorry, less than negative 1. Okay. But it's something which is bigger than 0, but less than negative 1. Alright. Now, therefore, if you are to rank from the most negative to the most positive, either use by this method, or you can substitute that force is equivalent to 1 and delta R is equivalent to 1 and tango with each angle. Alright, so you will find that the ranking from the most positive will start with C, the largest one, okay, followed by the here A, because it's 0, this is 0, this is positive, okay, double check with your values, yeah, and then followed by D, okay, why D? Because it started with a negative value, however, it's lesser than this one, okay? So check, okay? And you will find that B will be the most negative value you can get, okay? So I need you to try it on your own, but this time, go with substituting the number. If you are unhappy with this number, you can just change into some other number, 5 perhaps, okay? Any number would do. Now, in example 7.1, Mr. Clean here, we will find that the vacuum cleaner is our object of interest. And the guy is the environment. So it would turns out something like this. Work done by the man, because he is using his energy to pull, okay, to pull the vacuum cleaner, and by pulling the vacuum cleaner experience displacement, and later on you will find that it's also going to experience changes in its own speed, right? So how about normal force and weight? Okay, we will find that common sense tells us that displacement is occurring parallel to the surface. So this is where R occurred. Okay, R occurred in the same direction as delta X. And therefore, if the question is asking us work done by the force on the vacuum cleaner, so work done by the man on the vacuum cleaner, right? So it would sound something like this. This is the force, and F, and this is this displacement, which is just now they mentioned to the right, positive ke kanan, and 3 meter distance. And because of that, becomes force, just now, force times with the cos 30, because we want it to be parallel. So answer is 130. So 130 joule is being expended by this man. 130 joule telah digunakan oleh this guy to pull the vacuum cleaner. Understand? Alright. So however, it's also something to note that normal force and gravitational force is there. Force is there, motion occurred, but it does not do any work because they are perpendicular. So keywords here is find out where is the displacement, and from there look at forces that parallel to the displacement. Now this is an example coming from different book. Okay. Now in this example you will find that there is more than one force will give amount of work. Okay. So let's have a look. Number one, before we look even at the question, okay, common sense tells us that displacement occurred here. So this is our delta R. Okay. And force that are perpendicular with displacement would not contribute to the work. So no work for this one, normal force. And work for by the gravity would as well be 0. So therefore work would be contributed by 2. Number 1, force applied by this man. And number 2, force applied by friction. Okay, now let's have a look. An Eskimo returning from a successful fishing trip pulls a sled loaded with salmon. Total are 50 kilogram, and the Eskimo exert a force of 120 Newton of force by pulling on the rope. Now, how much does he do on the sled? On the sled. So, object or system is the sled. Okay, he is the environment. If the rope is horizontal to the ground, horizontal, and he pull a distance of 5 meter. Alright, in the first scenario, there is no angle. There is no angle, meaning that the situation is purely force to the right, displacement is also to the right. So, a direct calculation where 120 times 5, or we can include angle, cos 0 will give us 600 Newton. Now, the second situation, how much work does he do if now the angle is 30 degree? So, this is the scenario. So, look at how the answer changes a little bit, where still 120, the same, 5, the same. It's just that we incorporate 30 degree here and resultant a number of work whereby a bit lesser as compared to without angle. Kan? Kalau dia parallel betul-betul, it means that all the force applied purely, semua akan tukar jadi work. Tapi bila dia buat at angle, we will find that sum of the force, in this case F assign theta, kan dia jadi product kan. We find that, oh, one is in the X direction and the other is in the Y direction. Only this one sahaja would do work. Yang ini tak do work, dia goes into waste. Membazir sahajalah. So 520 sahaja. The rest of 800 tu hilang. Okay. Is it 800 or less? Differences tu. Alright. Now the next one is, okay. Okay, this is a little bit higher. Alright, but never mind. At a coordinate of 12.4 meter, the Eskimo lets up on the applied form. Maknanya force dah tak ada. Ni dah tak ada A friction 45 Newton between the ice and the sled. Now bring the sled to rest at a coordinate position of 18.2. Maknanya bila friction start? Pada 12.4 and also 18.4. 18.4. So together differences diorang adalah 18.2 tolak 12.4. Okay. Now, question dia, how much friction does this friction do on the sled? Meaning that throughout the distance of 18.2 meter ni sampai 12.4 meter, dia dah lepaskan tangan. Lepaskan tangan and therefore benda ni slowing down. Slowing down. Okay. So macam kat sini ada cerita dia yang behind that I haven't yet discussed, that when you pull an object with a certain force and a work is applied, you will find that object akan experience changes in the velocity. And then the moment you take away that force, velocity dia akan berubah lagi lah. In this case, because of the friction comes in, considered, you will find that the system akan stop. But nevertheless, what most important is, if we can sketch again the situation. So this is the sled just now. The movement occurred to the right, okay? Delta R is still to the right. Notice that they are using X, no problem. As long as you understand that delta X and delta R are the same. And friction is in this direction, opposite to the motion. And it's kinetic. And because of that, there is an incorporation of cos 180. And this cos 180 is the reflection of the negative just now. Okay? So meaning that if you are to write down the way we learn, 45 times 18.2 minus 12.4 times cos 180 because of the angle between force and the displacement. Then you will arrive with negative 261. Alright, 7.3. Okay, to understand more on how to operate using concept scalar product of two vector. Alright, given that you have a dot product, okay, number one, if you write or calculate work between A and B, okay, they are supposedly called dot product. Okay, now a dot product, you have seen earlier that when we do calculation of work, it must turns out to be F times R cos theta, so that they are parallel with one another and the angle of cos is between them. Okay, so another way to note is, so that you remember, F delta R and the angle must be in between them, and therefore it turns out to be cos theta, so that they are parallel. So in short, dot product is a parallel sama arah, parallel or anti-parallel. And in the case of just now, okay, FR cos theta can as well be written as F dot delta R. Okay. Okay. Now something to ponder or recall from your maths class. Okay, a dot product can it can be anytime written in any way around. Okay, meaning that you can write it as okay, we tend to write F times delta R, but it's also correct to write it as delta R, okay, dot F. Okay, bear in mind both are forces, yeah. Both are vectors. So you can just change them. Okay, no problem. You will still end with the same answer. And to note that, you can factorize them. And this is the factorization coming from this concept. Okay, you can factorize them provided that they are in the same direction lah. Okay, but nevertheless, okay, it's also important to note that a dot product of I times I hat and J times J hat, K times K hat, okay, is equivalent to 1. Why? Because they are in the same direction. So you find that the most simplest way to understand it is, it turns out to be cos 0. Okay, their angle and 0 with one another. That's why the angle turns out to be the product of cos theta becomes 1. Okay. However, when they cross with one another, cross maknanya y components times dengan x component. Okay, macam ni kan. This is the x component, this is the y component. Definitely you get 0 because earlier we did mention that they must be parallel. So any vector, the two vector of force and R should be parallel with one another. Okay, should be parallel with one another. Alright, in another way of writing in the maths class, okay, when you have two vector A and B, and therefore the dot product of A and B should be A dengan A but in X only, Y and Y, Z dengan Z, Z dengan Z. Alright, right, then only is a dot product. Understand? And finally, okay, if you have A times A, it means that all the X components, square them, Y components, square them, Z components, square them, you end with the same A squared, kan? Alright, to reflect on the concept of the scalar product, you are given A and B as given, okay, and you were asked to calculate the scalar product of A dot B, okay, dot B, A dot B. Alright, if you can still remember the earlier concept, what you must do is, you must times I with I, and then J with J, and then add them together. So altogether 2 times -1 is -2, then plus with 3 times 2, which is 6. So you have the answer as equivalent to positive 4. B, find angle between A and B. Alright, you have two options actually. The first option is by looking at the figure, which is a little bit harder. So A just now is 2, 3. So 2 and 3. So this is 2. This is 3. So this is A. B just now is -1. This is B. -1 and 2. So -1 and 2. Here. So this is B. Alright. So when you simplify, the figure should look something like this. This is B, the combination of the red one. And this is A. Okay. So this should be the angle between them. However, this would be a bit tough. So why don't we look at the calculation in the form of, okay, this way. Okay, if we write it in the form of the expression AB cos theta is the original vector times B, the dot product, or we tend to write it as this is work, and this is the force times delta R, and then the angle between them, Alright, now we did have this F and R, okay, F and R, whereby they did mention earlier that as an individual, okay, it's for instance A is 3 and 2, okay, 3 and 2. So this one, 3 and 2 need to be combined, okay, because this is the vector itself, okay, So 3 and 2 becomes square root 13, and B itself singularly is square root 5, right? Square root 5. So this is 13. For instance lah, this is just an example to let you see in the version of work, and R is square root 5. But the combination of work is the one that you have calculated earlier, which is 4. This is 4. And that's the reason, in order to get the angle, becomes 4 divided with square root 13 and square root 5. Okay, 4 divided by square root 13 and square root 5, leaving your answer as 60.3 degree. Okay, however, what we seen here is actually how we relate with the concept from the mathematical view. Alright, in example 7.3, again we are going to see the concept of the mathematics, okay, when we apply or using dot product. So here we are given delta R and F, okay. So we find that the R displacement occurred in the X and Y direction, and also force applied in the X and Y direction. On whom? On a particle. So this is our system. Particle is our system or our interest. Okay. So that's why the question, calculate work done by the force on the particle. So what happened to the particle? Now, in the sense of what we seen earlier, 2 times 5. Okay, 2 times 5. 2 times 5 plus, okay, 2 times 3. Okay. So altogether, 5 times 2 is 10. Okay. 3 times 2 is 6. Okay. And the answer is 16 joule. Now, in the situation where we have varying force is not constant, then we can't use the expression earlier that F dot delta R can be used. Okay. Why? Because force need to be constant. Now, therefore, what we need to opt is by using graph methods. Why? We seen earlier in the concept of differentiation and also integral, the fact is if we integral f towards dx, we are going to get the area under the curve of graph f versus x, right? And the area is equivalent to the amount of work, okay, the amount of work. So that's one. So the shaded area, all right? And in that sense, all right, this is an example of how we can do it, right? So you are given a situation where the motion of the particle travel from 0 until 6 meter, right? And calculate the work done by the force on the particle, total work. So total work should be equivalent to the whole area shaded here. And in that case, 5 times 4, okay? Consider the direction as well, okay? Don't see the direction here, madam. Alright. In the case that the direction is negative, you will or the direction of force is negative, you will find that the graph would be somewhere below here, right? So this is the case or the scenario where work would be negative. But in this case, this is a positive work and this is positive work. So 5 times 4, 4 is 20 joule. And here is 5 times 2. 4 and 6 is 2. So 5 times 2 times 1 over 2 is just 5. So altogether should be 20 plus 5. And yes, the answer is a positive product of 25 joule. This is another example where we will find that work can be negative in value. Alright, so according to the question, based on this figure, so find work by the force on the particle as it moves across the following distance, 0 until 8. Alright, 0 until 8, so this is 2, 4, 6, 8. Alright, 6, 8. This is 8. This is 8. So the area under the curve should be 1 over 2 times x and times 6. So the answer becomes 4 times 6, 24 joule. Right, 24 joule. Now, how about 8 until 12? 8 until 12 occurred here. Just between CE. Okay, CE. So 8, 12. So this is 8, 12. So this is the work that I have mentioned earlier that it can be a negative value. So 12 minus 8. So this is delta R. And times the force, which is negative 2. Sorry, not negative 2. Negative 3. Negative 3 and 1 over 2. So the answer is this is 4. Therefore, negative 6 joule. Alright, negative 6 joule. Now, if the question, this is the best question. It used to ask this question. What will be the total work done? So this question, total work done from x0 until the end of the motion, which is 12. So this is work total. When it involves work total, regardless how the motion goes to the right or to the left, it's all about adding up all the numbers because this is scalar product. So you are expected to add negative 6 just now with 24. Okay, with 24. So it should be something like this. Adding up all the numbers. So becomes, the answer is 18 joule. Now, even though we tend to write as half kx squared as a singular expression, we might get a little bit confused when it involves there is a displacement, right? So in the case of the derivation, they put that the final position is at 0 and the initial is at the negative x maximum, right? So when we generalizekan equation itu, kan, generalizekan dia, katalah kita kata motion initial dengan final, dia punya limits. In that sense, we will see something a bit different here. That you will find that calculation of work by the spring, okay, should be work initial, tolak work final. Alright, work initial minus work final. Take note of this one. Alright, work by the spring. Okay, let's keep this away, and then we are going to go back later. Now, example 7.5. A common technique used to measure the force constant of a spring is a demonstration set up as figure. There was this spring hung vertically as this, and then an object of mass m is attached to its lower end. Under the action of the load mg, the spring now stretches a distance d from its equilibrium. If a spring is stretched, okay, the d is now 2 cm by this mass or by this object, which is 0.55 kilogram. What is the force constant? Now, if we look at the free body diagram, force of the spring is going towards the equilibrium. That's the reason. This is where the equilibrium. X0 is here. So that's why force by the spring is upwards. The weight remain downwards, okay? By right, if it's not here, then we will find that a singular force in this direction, the spring will keep on moving downwards. So tak logik lah pula kan? So the balance is because dia stay static because there is an upward force by the spring. So from here, force and they are static. That's the reason why they are equilibrium zero. Static Jadi kita nampak Fs is equivalent to 0, and from there, recall back that Fs itself is negative Kx, alright, or Kx lah. Okay, negative is a representation of sifat, character dia nak pergi pada equilibrium. So at any time sebenarnya nak buang pun tak apa. So that's the reason why writing it as Kx or Kd here. Kx or Kd. And solving, you akan dapat the key constant as given. Right? Now, if the question now asking related to this topic, dia kata work by spring. Work by siapa? Siapa buat kerja? It was the spring. So, we are now going to use the concept of initial minus final. Initial minus final. Spring memang agak ganjil. Alright? So, the initial of the spring is 0. Okay, the initial is 0. Initially there is no displacement. And finally, there is a displacement stretching. Okay, so you find that work by the spring is negative 5.4 to the power of negative 2. It's also something to note as well. Okay, the displacement is occurring in this direction. Delta R is occurring in this direction. While the force is directed upwards, they are in the opposite direction. So it makes sense that the work by the spring is a negative product. Okay, the negative product. And you find as well, in the sense of asking what is work done by the gravitational force, it's the same. A positive value is a positive value. However, the value is a bit different. Look at how they calculated it. Mg, so this is M, this is M, this is G, and this is the displacement. But something to note is that this is where the displacement D just now, or delta R just now, and this is the direction of the gravitational force. They are of the same direction, and observe that it's a positive sign. Okay, positive sign. However, you might be surprised in terms of the number, they are slightly different. So we are going to do a little bit of exploration in the next section. Alright, let's now reverse a little bit, page 160. This is trying to understand what will happen to the F, okay, if let's say that the question is asking for the external force, right? Now, this is what happened when you apply force, okay, you apply to the left, for example, and due to that, you have the spring force acted in the opposite direction, okay? Maknanya kita tolak ke arah kiri, kita yang apply, but spring force nak pergi pada equilibrium. So that's the reason why the spring force is directed to the right. Dalam keadaan if the figure is reverse, keadaan pun akan reverse jugalah. Okay, maknanya katalah object now is being stretched. Okay, stretched, maka kita akan nampak F spring negative pula and force applied is positive. Okay, by using this figure. So, issue that the one that which is important for you to note in the concept of Newton's law lah, that the force apply ni and the Fs ni is equal in value, except that they are in the opposite direction sahaja. And because of that, if you are asked to find work external ni by the applied force ni lah. Okay, due to applied force, kita sebut applied force. Applied force as in the figure, ya. Applied force tu U lah. Maknanya you pull it, you push it. And due to that, ada correspond to the force by the spring, which is restoring force, S tu. Okay. And you will find that the equation slightly just terbalikkan sahaja of the spring. But they are of the same value. Nilai mereka sama sahaja. Cuma cara calculate tu sahaja berbeza. Alright. Alright, let's look at question 18 from the additional example. In this example, you will find that the spring used on the bow very much similar to the behavior of spring constant. Okay, so at an archery event, a woman draw the strings of her bow back towards her lah, 0.38 meter with a force that increases steadily. So this is to reflect that the force is not constant, from 0 until 215. What will be the equivalent spring constant, which is K value? So this is quite easy lah. The maximum K constant times the maximum displacement. Alright, maximum force applied divided by the maximum displacement. So you arrive with 566 Newton per meter. Now, how about how much work? Okay, now you can opt either to use half kx squared. Okay, you can use half kx squared. Does the archer do? It was she does it. Okay, she does it. So it's not work by the spring. It's not by the string. Sorry. Okay. So you could use half kx squared, or you can use these methods. Okay, you would arrive with the same answer. In the case here, what really happened is they find the average force, okay, the average force, and then times the displacement, okay, times the displacement. So arriving with 40.9 joule. Now, I like you to try by using, what if you are using this version, half kx squared. Will you arrive with the same answer or not? Alright, so previously, you have seen how to calculate work by using, in fact, 3 methods. Number 1 is by concept F and R must be parallel or anti-parallel. Therefore, you arrive with F delta R cos theta. Number 2, when you have a spring, okay, so the expression becomes changes in half k d squared or half kx squared. So it should be initial minus final if we are talking about work done by the spring itself. And another 2 notes is work by the frictions. Okay, that work by the friction is angle involved is 180. Yeah. Here onwards, okay, here onward is where we're going to go a little bit deeper and combine with an idea that you have seen in the previous topic, which is, okay, the work can now be combined with an expression. We call it as kinetic equation. However, what is this kinetic equation? Kinetic is half mv squared, okay. Kinetic energy is half mv squared. Generally, you will find that work can be calculated by using this 7.15, that change in the kinetic energy is equivalent to the work external. Now, a bit confused here in terms of the external. Don't worry so much. The external is actually referring to the force applied. So this is change in the kinetic energy. So usually referring to the applied forces. Okay. Alright, let's have a look at equation 7.17. So the same thing that I mentioned earlier, that work external, here is the applied force, is actually as equivalent to the change in the kinetic energy. And let's say the expression, okay, they ask you, okay, please solve this by using work energy theorem. So the expression that involved is actually the amount of work that you have calculated is equivalent to change in the kinetic energy. By the way, alright, this expression is the generic expression. Bear in mind that you can calculate the work as well by using the expression of F times R cos theta. And recall again that F and delta R must be parallel or anti-parallel. And make sure as well that both are vectors. Yet the answer of the work value tu is a scalar value. But again, okay, we would like now to recall or to understand more on what it meant by, if let's say, if we did calculate and arrive with a positive value, what does it mean? Okay, so here it says that it means that kinetic energy increase. Increase means the speed is getting larger. If it's decrease, it means that negative work means that energy now is transferred out of the system. We can say that friction is here. Okay, most probable friction is here. Alright, you have seen earlier the concept of work that it can be negative, it can be positive, and must be calculated by using constant value times the displacement, and they must be parallel or anti-parallel. For that, we are using the approach of dot product. Okay, now, for a spring, however, would be a little bit different. Okay, now if you can recall from what you have learned in high school, that spring force or spring force is a product of negative times k times x, where k is a constant. Okay, the force constant is just to reflect that it's not force lah, yeah? It belongs to the force, alright, to the spring or spring constant. Alright, here, okay, this is trying to show you how when we plot a graph of f versus x, we are not going to arrive with a flat curve. Why? Number one is because of the direction of the force. The force, spring force here, we call it as a restoration force. It's not here. Okay, restoration force. Okay, restoring force. Restoring force try to say is that when you pull it to the right, like this instant, it also represent it will meant to pull it back to the equilibrium. Okay, maknanya dia nak duduk stabil. This is where it should be. Tapi you disturbkan dia. Jadi what happen? Bila you release the spring will tend to pull mass together with the mass back to the equilibrium. Jadi, you find that displacement is in positive direction. Okay, macam ni ha. Displacement is positive direction. However, dia punya force is a negative value. Jadi, you find the shape of the graph is a bit like an incline. Okay, and to repeat again the process, okay, for instance, this third figure, when you compresskan dia, okay, you find that after you release kan, the force tu akan ke kanan. Why? Because dia akan go back to the equilibrium. Because the idea of a spring, it always try to go back to the equilibrium. Okay, ni ingat-ingat lupa lah from high school. Tapi that's the idea of the restoring force. Restore, cuba nak balik pada asal. So, you find that the displacement and also force are always opposite to one another. Nampak? Yang ini to the left, and then force dia positive value. Negative displacement, but force is positive directed to the right. Okay? And in short, you have a triangle to indicate the area of work. Work dia adalah a triangle. Triangle. And because of that concept, if we go back by the version of integral, okay, by the integral f towards the displacement, you find that you end up that work is a half kx squared. Itu nak pakai sebenarnya. That work for a spring, work for a spring adalah half kx squared. That's it. Alright, now we are going to look at example 7.6, but let's say that you are referring to other book as well. You will find that this is another terms used by other books. Work net, okay, work net, work total. So you will see that this is very similar to work external force, because why? When you do the calculation of work net, you are actually considering net force times dr, where together with cos theta, alright? But the idea is this force is actually the applied force. This is F applied as well. Okay, so this is the case whereby if in case you did refer to other textbook, it has the same connotation. Okay, now by looking at example 7.6, this is a scenario whereby there is no friction. Okay, it does say that it's frictionless, and the blocks involved, mass is 6 kilogram. Pull to the right as in figure, horizontal surface. So it means that this is the displacement. Alright. A little bit so that it maps equal to something we learn here, delta x, and this is as well delta r, therefore. So the question, if let's say that the force is constant, has a magnitude of 12 Newton, they want you to determine the block speed, the V final, after it moved through a horizontal distance of 3 meters. So this is our delta R or delta X, yeah. And something, okay. So it starts from rest. So this is the initial. Now, related to the, when it starts asking for speed, or in fact velocity, there's nothing wrong if it does asking you for the velocity, then by right, we are now considering the concept of work equivalent to change in the kinetic energy, or by this book, they tend to write it as change of K. So they have the same meaning, okay, have same meaning, but it's just that the way they write it is different. So let us now look at the expression, okay. So you will find this is the expression we are looking for, work energy theorem. And bear in mind work external here represent that the net force, okay, external or applied force times the R or X, and they must be with an angle, parallel with one another. In this case, since according to the figure, the force applied with the displacement with the motion are parallel. So they give you a product of cos 0, and force here just now is a product of 12 Newton, okay, and to the right, so that's why it's positive. Displacement is also a positive product, and because why it moved to the right. Okay, so simple. And then substituting the kinetic energy, so this is the V that we would like to determine. And the kinetic energy for the beginning is 0 because object initially is at rest. So from here, we are going to arrive with the V final as a 3.5 meter per second. Now from example 7.6, I like us to go a bit backward, which is quick quiz 7.5. In this quick quiz 7.5, we need to use this expression belonging to spring, where work external by force applied to a spring would be equivalent to a product of half kx final squared minus, or perhaps we can factorize, x initial squared. Okay. Now, the situation is originally a dart spring inside it is compressed, okay, by a distance of x. The next loading, the distance is now double. So they want you to compare how much faster the second one, okay. So what we did is we are going to divide equation with the equation. However, important to note that when we substitute the initial, okay, in the case when x, okay, for this one, when we substitute, the situation is started with initial 0, and then the final version is x alone, Okay, how about when it's 2x? Okay, this is the expression for this one. Okay, we find that half k, but the final is 2x. So this is the x final for the second situation. And initially it doesn't stretch or it doesn't compress. Okay. Why is it that it doesn't say so? Well, it should say so. So this is my part to explain to you. Alright. Now, what we did is, we are aware that both expression, okay, let's complete this expression, is also equivalent to the change of kinetic energy. So, change of the kinetic energy, I am tempted to write it as KE. The book tend to write it as change of K, both the same, right? And this is equivalent to half mass V squared minus U squared. Alright. Now, bear in mind, the system is originally doesn't move. Okay, doesn't move. So, V squared minus kinetic energy, which is 0. Why? Because U is 0. Now, it goes the same for this one. Goes the same as this one, where half m V squared, but minus as well 0. Okay, so this is a situation for when x alone, okay, displacement is x. This is a situation when displacement is 2x. So we are going to divide these two expressions. How to divide? Okay, just take the final. Okay, usually I am tempted to put it this way: half k for x squared. Alright, equivalent to half mv. Okay, I'm gonna put it as 2x so that we don't get confused. Then let's divide with the red one, the original situation, kx squared, and divide equation with equation, meaning that left and right are to be divided with the same thing. So half mass v for x. Now let's simplify it. So, well, half, take away k. This is x, the same thing. Half, and then mass. So we are left with 4 equivalent to v for the second situation, okay, to x squared, over with the original situation when the compression is only x. What we now did is, we are going to take away the square root. So, it will looks like this. So, the situation when you compress it double, it turns out to be, this turned to be 2. So, 2 of the original, if let's say the compression is only a distance x alone. So, in short, that's how we say is that it 2 times as fast. Okay, 2 times as fast. Let us now look at page 164, conceptual example 7.7. In this example, we are going to see whether the amount of work is equal, less, or larger by using two methods. Either number 1, through the incline or through the ramp. So this is number 1. Or through here, through the vertical climb. So in this calculation, we will arrive that they have the same amount of work regardless of the methods. Why? Okay. The reason is because we will find after this the concept involved called conservative force. However, it's not going to be introduced here. It will be in chapter 8. Alright. Let's now have a look at the example.